A man is dying in a guarded room at Walter Reed Army Medical Center in Washington, and the guards are not there to protect him. They are there to listen. He is 53 years old. He is arguably the most capable mathematician alive, and the United States government is worried that under morphine he will start talking about weapons design in front of the nurses. He is passing the time reciting Goethe from memory, page after page in German, from a book he read as a child. And the thing coming apart in that room, slowly, over about a year and a half, is the exact thing he had proved 25 years earlier, that physics cannot function without. That happened February 1957, and the proof he left behind has never been broken. In 1932, John von Neumann traced a measurement as a physical process. Particle, detector, light across the room, your retina, your optic nerve, your visual cortex, and he showed that the equations never stop anywhere along that chain. Nothing collapses. The superposition just keeps spreading. And the boundary where the quantum world ends and your world begins can be placed at any link you like, with no experiment in existence able to tell the difference. Tonight we follow that chain the whole way down. Through Grete Hermann catching an error that nobody read for 40 years, through Wigner putting consciousness into physics and then quietly taking it back, through the Decoherence papers whose own authors state in print that they did not solve this, through Everett and Bohm, and down to a germanium detector buried under an Italian mountain that killed the most elegant answer anyone has ever proposed. By the end, you will understand why every route out of this costs something enormous, and why the chain still terminates exactly where von Neumann said it does. Get comfortable and stay to the end, because the last 20 minutes are where that chain arrives at you personally. If you want these without ads, that is what Meridian Labs is, the Patreon behind this channel and a handful of others like it. Ad-free episodes across every participating channel, early access before they go public, and an audio-only feed for listening with the screen off. Subscribe or join if you have not. Let's start where it started. There is a proof, published in Berlin in 1932, still standing, never refuted, that says the boundary between the quantum world and the world you are sitting in right now can be placed anywhere you like. Inside the detector. Inside the air between the detector and your face. Inside the lens of your eye. Inside your optic nerve. Inside the visual cortex at the back of your skull, 3 centimeters behind your ears. And no experiment ever in any laboratory using any technology will be able to tell the difference. That is not a metaphor, that is a theorem. It was written by a Hungarian mathematician named John von Neumann, and it appears in chapter 6 of a book called Mathematische Grundlagen der Quantenmechanik, the mathematical foundations of quantum mechanics, which Springer published in 1932 and which is still, 94 years later, the formal skeleton that every quantum mechanics course in the world is built on top of. You have used its mathematics if you have ever taken a physics class. All of it is his, from Hilbert space to the density matrix to the projection postulate itself, and buried in the middle of it is the part nobody quotes. Von Neumann took the act of measurement, the single most ordinary thing a physicist does, and he traced it as a physical process. A particle hits a detector, the detector amplifies the signal drives a needle, or a pixel, or a click. Photons leave that needle and cross the room. They strike your retina. Your retina fires a chemical cascade down the optic nerve. Your brain builds a picture. And at every single link in that chain von Neumann showed, the quantum mechanical description does not stop. The superposition does not collapse. It spreads. The detector becomes entangled with the particle. The air becomes entangled with the detector. Your retina becomes entangled with the air. Your neurons become entangled with your retina. The equations do not break anywhere. The equations happily describe your own brain as a smear of possibilities, right up until the moment something outside the chain looks at it. Von Neumann proved that you can cut that chain wherever you want. Cut it at the detector and say the collapse happened there, and the mathematics gives you one set of predictions. Cut it at your retina and say the collapse happened there instead, and the mathematics gives you exactly the same predictions. Move it again. Put the cut between your optic nerve and your visual cortex. Same predictions. Put it between your visual cortex and whatever it is that constitutes your awareness of seeing. Same predictions. Every possible placement of that boundary is empirically identical to every other, which means the theory that we use to design transistors and lasers and medical scanners and the entire semiconductor industry contains, at its foundation, a free parameter that physics cannot fix and experiment cannot measure. And the chain has to be cut somewhere. Because you do not experience a smear, you experience one result. Von Neumann was completely explicit about where he thought the chain ended. He wrote that the description must terminate in what he called the subjective perception of the observer, not the detector, not the brain, the perception, the place where the physical account runs out and something else takes over. He was not being mystical about it. He was doing bookkeeping. He had a principle he called psychophysical parallelism, the requirement that anything you experience subjectively must also be describable as a physical process, and he was trying to save it. The problem is that saving it meant admitting that the physical process never ends on its own. Something outside it has to close the account. He was 28 years old when he wrote that. I want to be careful here, because this is the exact point where this story usually gets stolen by people who want it to mean that your mind creates reality, and that is not what I am telling you. It is very close to what one Nobel laureate ended up saying out loud in 1961, and we are going to get to him, and we are going to get to the part where he took it back. But the actual situation is stranger and much more uncomfortable than consciousness creating reality, because consciousness creating reality is at least an answer. What von Neumann left behind is not an answer. It is a hole with a proof around it, showing that the hole cannot be filled from the inside. Physics has spent the last 94 years trying to fill it anyway, and I want to walk you through every single attempt, because every one of them failed in a different and more interesting way than the last. The consciousness route failed, and the man most famous for taking it publicly abandoned it. The decoherence route, the one you have probably heard is the modern solution, did not solve the problem, and the physicists who built it say so in print, in journals, in sentences you can go and read tonight. The many worlds route requires you to accept that there is no such thing as a probability. The pilot wave route requires you to accept faster than light influence as a structural feature of reality. The spontaneous collapse route requires new physics that experimenters are currently in the process of killing, and in 2020, they killed one of the most elegant versions of it using a germanium detector buried under a mountain in Italy. None of them worked. And this took me an unreasonably long time to understand while I was reading through this material. They did not fail because physicists were not clever enough. They failed because von Neumann's chain is not a puzzle inside physics. It is a statement about the shape of physics. It says that a theory built entirely out of continuous evolution cannot, by itself, ever produce a single definite event. Not with more mathematics, not with better equipment, not ever. And a single definite event is the only thing you have ever experienced. There is a sentence that John Stuart Bell wrote in 1990, in a paper he titled Against Measurement, and it is the most contemptuous thing I have ever read in a physics journal. He was attacking the way textbooks treat the word measurement as if everybody knows what it means. He wrote, "Was the wave function of the world waiting to jump for thousands of millions of years until a single-celled living creature appeared? Or did it have to wait a little longer, for some better qualified system with a PhD?" He was being sarcastic. But he was not making a joke, and he had no answer of his own to give. Bell spent his entire career on this, made himself the most important figure in the foundations of quantum mechanics since the 1930s, and he died in 1990 of a cerebral hemorrhage at 62, with the question exactly as open as von Neumann had left it. The chain is still there. Every physicist knows it is there. It sits underneath the most successful theory in the history of science, the one that predicts the magnetic moment of the electron to 12 decimal places, the one that made the device you are using right now physically possible. And it says that somewhere between the particle and your awareness of the particle there is a step that the theory does not describe and cannot describe, and that we have no experimental way of finding out where it is. And that is the polite version. The impolite version, the one that took me weeks to be willing to write down, is that the terminus of the chain. The thing von Neumann needed to exist in order for physics to close has never been defined by physics at any point in its history. There is no equation for it. There is no measurement of it. It appears in the axioms of quantum mechanics as an undefined primitive, in exactly the same way that a point is undefined in geometry, and everything else in the theory is built on top of it. That undefined primitive is you. Hold on to that. We are going to come back to it in about 2 hours, and by then it is going to mean something considerably worse than it means right now. Budapest, 1913. A 10-year-old boy is walking through the Fossori Lutheran Gymnasium with a copy of a 44-volume German history of the world, and he has memorized sections of it well enough to recite them back on demand, in the original, decades later. His name at that point is Neumann Janos Lahos. His father is a banker who bought the family a title, which is where the von comes from. The school he is walking through will, within about a decade, also produce Eugene Wigner and Leo Szilard. And a little further out in the same few square kilometres of Budapest, Edward Teller and Dennis Gabor and Paul Erdos. There were so many of them, and they were so far outside the normal distribution, that the physicists at Los Alamos eventually started calling them the Martians, on the theory that a Hungarian was simply an alien who had learned to imitate a human being with a slight accent. Von Neumann was the most alien of them. Hans Bether, who was not a modest man and did not hand out compliments casually, said that von Neumann's brain indicated a new species, an evolution beyond man. His party trick was that he could be given a problem in the middle of a conversation and produce the answer before anyone else had finished writing down the terms. He worked out the mathematics of shaped charge implosion for the plutonium bomb. He built the architecture that every computer in the world still uses. He invented game theory. He wrote the founding paper of Self, replicating automata. And in 1927, at 23 years old, he published 3 papers in the Göttingen Nachrichten. The Proceedings of the Göttingen Academy of Sciences, that took quantum mechanics from a collection of brilliant guesses and turned it into a rigorous mathematical structure. Because that was the actual state of the field. This is the part that gets flattened in the popular telling. In 1927, quantum mechanics existed in 2 rival forms that nobody could reconcile. Heisenberg had matrix mechanics. Schrödinger had wave mechanics. They gave the same answers and looked nothing like each other, and Dirac had produced a formalism that worked beautifully, but relied on a mathematical object, the delta function, that did not exist as far as any mathematician was concerned. Von Neumann came in and rebuilt the entire thing on the theory of operators in Hilbert space. He showed that matrix mechanics and wave mechanics were 2 representations of the same abstract structure. He gave the theory the spectral theorem. He introduced the density matrix, which is how physicists still today describe a system when you do not have complete information about it. He put the whole apparatus on foundations that have not moved since. And then in 1932, he collected it all into the book. And having built the machine, he did something that almost nobody who builds a machine ever does. He turned it on the machine itself and asked what it says about the act of using it. Here is what he found, and I want to go slowly because the logic is airtight, and the conclusion is genuinely difficult. Quantum mechanics contains two completely different ways for a state to change over time, and von Neumann labelled them process 1 and process 2. He put process 1 first, which tells you something about how central he thought it was. Process 2 is the one you learn about. It is the Schrödinger equation. It is continuous, it is deterministic, it is perfectly reversible. And if you know the state of a system now, it tells you the state of that system at any point in the future or the past with total precision. Nothing is lost, nothing is random. If you could write down the wave function of the entire universe and let process 2 act on it, the future would be as fixed as the past. This is not a controversial claim, this is the actual content of the equation. Process 1 is what happens when you measure something. It is discontinuous. It is irreversible. It is probabilistic rather than deterministic, and it is the only place in the entire theory where probability enters at all. A system in a superposition of two states is suddenly in one of them. Information is destroyed. The other branch is simply gone. And crucially, and this is the part that cost von Neumann whatever peace of mind he had on the subject, process 1 cannot be derived from process 2. It is not a special case. It is not an approximation. It is a second, separate, foreign law that has to be bolted onto the theory by hand, and the theory gives no account whatsoever of when to apply it. Think about what a strange thing that is to find in a physical theory. Imagine if Newtonian mechanics had a second law that said, and sometimes, under conditions we will not specify, objects teleport. And imagine that law was correct, that it matched every observation, and that the entire edifice of physics collapsed without it. Von Neumann proved that these two processes cannot be reconciled. He showed formally that if you take a quantum system and a measuring apparatus, and you let process 2, the honest continuous physics, act on the pair of them, you do not get a measurement outcome. You get an entangled superposition of apparatus states. The needle pointing left and the needle pointing right, both together in a single state. Modern philosophers of physics call this von Neumann's insolubility proof, and it has been strengthened many times since, and it has never been broken. Unitary evolution, applied to a system and a device, cannot produce a single definite pointer reading. It is mathematically incapable of it. Which leaves you with a straightforward problem. The needle does point one way. You have looked at needles. They point. Therefore, process 1 has to happen somewhere. And von Neumann went looking for where. This is where the chain comes in, and where the book stops being a mathematics text and becomes something closer to a philosophical hand grenade with the pin left in. He set up the sequence. Take a system, call it 1, the thing you want to measure. Take an apparatus, call it 2. You can treat 1 as quantum and 2 as classical, apply process 1 at the boundary between them, and you get correct predictions. Or, he showed, you can take both 1 and 2 as quantum, let them evolve together under process 2, and then place the boundary between the apparatus and the light, travelling from it to your eye. And you get exactly the same predictions. Or you can absorb the light into the quantum description too, and put the boundary at the retina. Same predictions, absorb the retina. Put the boundary at the optic nerve, same predictions. Absorb the optic nerve, the chemical cascade, the firing of ganglion cells, the transmission into the lateral geniculate nucleus, the arrival in primary visual cortex. Put the boundary anywhere in there, same predictions. Every placement is empirically equivalent. That is the theorem. And it is a theorem, not a suggestion. The invariance of the predictions under displacement of the cut is a mathematical property of the formalism. Now here is the move that makes this an argument rather than an observation. A reasonable person reading that result would conclude that the cut is a bookkeeping convenience with no physical meaning. Put it wherever is easiest, get on with your day. And that is broadly what working physicists do, and it works fine, and it has worked fine for a century. But von Neumann understood that the convenience is exactly the problem. If the cut were a real physical event, a thing that happens at a particular place, then moving it should change something. Moving a real physical process into a different piece of apparatus should have consequences. It has none. Which means either the cut is not a physical event at all, in which case you have to explain why you experience one outcome, or it is a physical event that reality has arranged to be permanently and structurally invisible. Neither of those is a comfortable thing to have at the foundation of your best theory. And von Neumann drew the conclusion that the chain must terminate outside the physical description entirely. He wrote that the boundary can be pushed arbitrarily far into the interior of the body of the actual observer, but that experience only makes statements of the following type. An observer has had a certain subjective perception. Never anything like this. A physical quantity has a certain value. His argument was that since the boundary can go anywhere, and since something has to end it, the only place it can genuinely end is at the one point in the sequence that is not a physical system at all. The point where a physical process turns into somebody's experience of that process. He was not saying that the mind reaches out and changes the particle. He was saying something more careful and, I think, considerably more disturbing. He was saying that quantum mechanics, taken at its word, describes the entire universe, including your nervous system, as an unbroken web of superposition, and that the only thing in the account that ever registers a single fact is the observer, and that the theory has nothing to say about the observer at all. He put a hole in the foundation, and then he proved the hole was load-bearing. I have read chapter 6 3 times now, and the thing that gets me is not the argument. The argument is clean. It is the tone. There is no drama in it. He is not trying to shock anybody. He works through the formal structure of measurement with the same flat competence he brought to operator algebras, arrives at the conclusion that physics terminates in consciousness, notes it, and moves on to the next section. A man who could hold 44 volumes of world history in his head wrote down the most metaphysically explosive result of the 20th century in the voice of someone filing a tax return. And then the field did something remarkable with it. It ignored the chapter completely and spent the next 35 years using a different theorem from the same book to shut down anyone who tried to fix the problem. That theorem is the reason you have never heard any of this. And the story of what happened to the woman who refuted it 4 years after it was published is the first of several places in this where I stopped taking notes and just sat there. Elsewhere in the same book, in a much shorter and much more famous passage, von Neumann proved that quantum mechanics cannot be completed by hidden variables. The claim is this: suppose you think particles really do have definite properties all the time, and the probabilities in quantum mechanics only appear because there are underlying variables we cannot see. Einstein thought this. De Broglie thought this. It is the most natural thing in the world to think, and it would dissolve the measurement problem instantly, because if outcomes are already determined by variables you cannot access, then nothing needs to collapse. The needle was always going to point left. You just did not know it. Von Neumann proved this was impossible. Formally, rigorously, in the same book that had just put the whole theory on unassailable foundations, written by the most respected mathematician alive. And the effect on the field was total. For 3.5 decades, from 1932 until the mid-1960s. If you were a young physicist who found the measurement problem unbearable and wondered whether there might be a deeper layer, you were told, usually within about 90 seconds, that von Neumann had proved there was not. David Mermin, one of the sharpest writers in 20th century physics, described what that felt like from the inside. He wrote that graduate students were beaten into submission by the claim that von Neumann had proved that it could not be done. That is his phrase, beaten into submission. The proof was wrong, not subtly wrong, not wrong in a way that took new mathematics to expose, wrong in a way that a graduate student could find with a piece of paper in 20 minutes, resting on an assumption that von Neumann simply had no right to make. The assumption was additivity of expectation values. In quantum mechanics, if you have two observable quantities, the average of their sum equals the sum of their averages. That is a theorem, it is true, and von Neumann proved it himself. He then required that the same relation hold for the hypothetical hidden states, the ones where every quantity has a definite value at all times, and for those states it is obviously false rather than merely unproven, and the counterexample is embarrassing. Take the spin of an electron along the x-axis and along the y-axis. Each of them, when you measure it, gives you +1 or -1. Nothing else. Now take the combination of x and y spin divided by the square root of 2, which is a perfectly legitimate observable. It is what you get if you measure spin along a diagonal. That observable also only ever gives you +1 or -1. But if you demand that the values add the way the averages do, you get +1 or -1, all divided by the square root of 2, which gives you 0, or plus the square root of 2, or minus the square root of 2. It never gives you +1 or -1. The requirement is inconsistent with the measured spectrum of the operator on the first line of the argument. That is the load-bearing assumption of the theorem that suppressed an entire research program for 35 years. And somebody caught it. In 1935, 3 years after the book was published, a 34-year-old German philosopher and mathematician named Grete Hermann published a paper called Die naturphilosophischen Grundlagen der Quantenmechanik, the natural philosophical foundations of quantum mechanics, in a journal called the Abhandlungen der physischen Schule. She identified the additivity assumption. She said correctly that von Neumann had assumed exactly what he was setting out to prove, that the argument was circular at its centre, and that hidden variables remained entirely open as a possibility. Nothing happened. Grete Hermann was not a crank, and not an outsider to serious mathematics. She was Emmy Noether's first doctoral student, and Emmy Noether was the greatest algebraist of her generation, and the woman whose theorem connects every conservation law in physics to a symmetry. Hermann took her doctorate at Göttingen in 1926. She went to Leipzig and argued about quantum mechanics with Heisenberg and Carl Friedrich von Weizsäcker directly, in person, in the room. Heisenberg wrote about those conversations later. She was not shouting from the margins, she was in the building. And her paper vanished for close to 40 years. It was rescued from complete obscurity by the historian Max Jammer in 1974, more than a decade after the field had already independently rediscovered her objection. I want to be careful with this story because it gets told badly, and it gets told badly in a way that flatters us. The clean version is that a woman found the error, the men ignored her because she was a woman, and physics wasted 35 years. And there is real substance to that. She was a woman in Germany in 1935, publishing in a small philosophical journal in the middle of the Nazi rise, while she was simultaneously writing anti-Nazi articles under false names for underground socialist papers, which she did continuously from 1927 until 1940. Nobody was reading the Abhandlungen der physischen Schule for quantum foundations. But the flattering version is also not quite true, and a piece in Physics Today a few years ago made the point sharply. Her work was never completely forgotten in the German-speaking world, and reducing her to the woman who caught von Neumann's mistake erases what she actually cared about, which was the relationship between scientific knowledge and moral responsibility, a subject she wrote about for the rest of her life after the war while helping rebuild the German education system. She died in 1984. She lived long enough to see the field come round to her position and to receive almost no credit for having got there first, and as far as I can tell she did not seem to mind very much, which somehow makes it worse, because when it finally did land, it landed with somebody the establishment could not ignore. John Stuart Bell was a Northern Irish physicist working at CERN, a specialist in accelerator design who did quantum foundations on holiday, because in the 1960s that was the only responsible way to do quantum foundations if you wanted a career. he rediscovered Hermann's objection independently, and he wrote it up in a paper titled On the Problem of Hidden Variables in Quantum Mechanics. He wrote it in 1964. It was published in Reviews of Modern Physics, Volume 38, page 447, in 1966. Look at those two dates. The manuscript sat for 2 years. It was mislaid in the editorial process, which meant that Bell's demolition of von Neumann appeared in print 2 years after his own far more famous theorem about local hidden variables, in the wrong order, so that the paper explaining why the door was open arrived after the paper explaining what was behind it. Bell was not diplomatic about what he had found. In an interview with Jeremy Bernstein published in Omni magazine in May 1988, on page 88, he said this: "The von Neumann proof, if you actually come to grips with it, falls apart in your hands. There is nothing to it. It is not just flawed, it is silly." And then he said, and this is verbatim, "When you translate them into terms of physical disposition, they are nonsense. You may quote me on that. The proof of von Neumann is not merely false but foolish. You may quote me on that." He wanted it on the record. A man who had spent his career watching a field refused to ask obvious questions because of a theorem nobody had checked, and when a journalist finally asked him about it, he made sure the quote could not be softened. Now, in fairness, and because this audience will go and look it up, there is a live scholarly fight about whether Bell was right to be that harsh. Jeffrey Bubb published a reappraisal in Foundations of Physics in 2010, arguing that von Neumann never intended the sweeping claim that was made on his behalf, and that his real target was narrower. Dennis Dix has argued something similar. Mikhail Sievink and Jos Uffink have a paper reconstructing the proof sympathetically, and they point out something that ought to embarrass everybody, which is that Hermann herself noticed von Neumann obviously knew eigenvalues do not add, because he says so, which means the charge of stupidity was never the right charge. On the other side, Mermin and Rudiger Schack published a paper in 2018 with the title Homer Nodded, arguing flatly that the revisionists are wrong, and that Hermann and Bell understood exactly what von Neumann was doing. That fight is not settled. I do not think it is going to be settled. But here is what nobody disputes. Whatever von Neumann meant, the physics community used the theorem as a wall for 35 years, and the wall was made of nothing, and almost nobody in 3.5 decades of graduate teaching walked up and pushed it. And this is the misconception I need to correct, because it is the one that lets people file this whole story away as solved. When Bell took down the impossibility proof, an enormous number of people concluded that von Neumann had been discredited and that his measurement analysis went down with it. That is completely wrong, and it is wrong in the direction that lets you sleep at night. Bell demolished one theorem. The Hilbert space formalism stands. The spectral theorem stands. The density matrix stands. And chapter 6, the measurement chain, the arbitrary cut, the two irreconcilable processes, all of it stands, entirely untouched, and Bell knew it stood, which is why he spent the remaining 24 years of his life obsessed with it, and why he wrote Against Measurement in 1990, attacking the word measurement as unprofessional and imprecise and unfit to appear in the axioms of fundamental theory. The thing Bell destroyed was the argument for why we should stop looking. The thing he could not destroy was the reason we were looking in the first place. And there is one more thing about the 1930s that has to be corrected here, because it is the single most misunderstood image in all of physics, and it belongs to this argument rather than to the one people think it belongs to. Erwin Schrödinger published a long paper in 1935 in Naturwissenschaften, volume 23, spread across 3 issues, titled Die gegenwärtige Situation in der Quantenmechanik, the present situation in quantum mechanics. It is the paper in which he coined the word Verschränkung, entanglement, for the phenomenon of two systems that can no longer be described separately, and in the middle of it he describes a steel chamber containing a cat, a small quantity of radioactive substance with a 50% chance of one atom decaying in an hour, a Geiger counter, a relay, a hammer, and a flask of hydrocyanic acid. Everybody knows the image. Almost nobody knows what it was for. Schrödinger was not proposing that cats can be alive and dead simultaneously. He was attacking that idea. He described the scenario explicitly as a ridiculous case, and the whole purpose of the passage was to demonstrate that if you take the formalism seriously and apply it consistently, you are led to something absurd, and that the absurdity is a symptom of the theory being incomplete. It was a reductio. It was a weapon aimed at his own field, and it has been reproduced for 91 years as though it were a charming illustration of how weird quantum mechanics is, in the exact opposite spirit to the one it was written in, which I find almost funny and which I think would have annoyed him enormously. But look at what the cat actually is, structurally, and you will see it immediately. It is von Neumann's chain with fur on it. Atom, counter, relay, hammer, flask, cat, 6 links. And Schrödinger's point is precisely the one from chapter 6, which is that the quantum description does not stop propagating at any of them. There is no link in that sequence where the mathematics says, and here the superposition ends. The counter inherits it, the relay inherits it, the cat inherits it. Schrödinger picked a cat rather than a photodetector, for the same reason a prosecutor picks a photograph rather than a diagram, because he wanted the absurdity to be unignorable. 3 years after von Neumann's book, and independently, and from a completely different direction, the man who wrote the wave equation arrived at the same structure and concluded from it that something in the theory must be wrong. 1935 was a very bad year for the standard account. Grete Hermann demolished the impossibility proof. Einstein, Podolsky and Rosen published the argument that quantum mechanics cannot be both complete and local, and Schrödinger, in response to Eppra, coined entanglement and put a cat in a box to show that the chain has no natural end. 3 separate attacks on 3 separate pillars in 12 months, and the field absorbed none of them and carried on. The reason it carried on is that the mathematics worked. That is the whole story of this field in one sentence. When your equations predict everything you can measure to 11 decimal places, the pressure to fix the conceptual foundations drops to almost nothing, and the people who keep pushing start to look like they have a personality problem rather than a physics problem. Therefore the door was open again, and hidden variables were back on the table, and the obvious question was whether anyone would now walk through and close the chain properly. But the first serious attempt to name the terminus had already happened, in Paris, in 1939, in the last months before Europe closed, and the answer it gave was the one that has haunted this subject ever since. The man who wrote it had already lost one country and was about to lose another. Fritz London was born in Breslau in 1900 into a Jewish academic family, and by his late 20s he had done work that would have secured any career. In 1927, with Walter Heitler, he wrote the paper that explains the chemical bond in quantum mechanical terms, which is the founding document of the entire field of quantum chemistry. Every structural formula you ever drew in a school chemistry class rests on that paper. He went on to explain the weak attraction between neutral atoms, which is why the forces are called London dispersion forces. And later he produced the first successful theory of superconductivity and the first real theory of superfluid helium. This is a physicist of the absolute first rank. In 1933, the Nazi regime removed him from his position, and he left Germany. He went to Oxford. Oxford did not keep him. He went to Paris, to the Institut Henri Poincaré, and it was there, working with a French physicist named Edmund Bauer, that he wrote a short monograph called La théorie de l'observation en mécanique quantique, the theory of observation in quantum mechanics, published by Hermann et Cie in 1939 as number 775 in a series of scientific pamphlets. Then Europe fell apart, and he left for Duke University in North Carolina, where he stayed until he died in 1954, aged 54, of heart disease. He is not remembered for this pamphlet, he is remembered for superconductivity. but the pamphlet is where somebody finally said out loud what von Neumann had left implicit, and it says it with a directness that still stops me every time I read it. London and Bauer walk through the measurement chain exactly as von Neumann laid it out. System, apparatus, observer, all in one entangled state, no collapse anywhere, the whole structure smeared. And then they ask what is different about the observer, and their answer is that the observer possesses a characteristic and quite familiar faculty, which they call the faculty of introspection. He can look at his own state. He knows, directly and without measuring anything, what he is currently experiencing. And by virtue of this immanent knowledge, they wrote, he attributes to himself the right to create his own objectivity. To cut the chain of statistical correlations, read that again, to create his own objectivity. To cut the chain. That is 1939. That is not a fringe pamphlet from a mystic. That is a founder of quantum chemistry, writing in Paris while his life was being taken apart around him, saying that the reason the world contains facts is that a conscious observer looks inward, finds a definite experience there, and thereby severs the mathematics. Now I want to slow down, because there is a genuine ambiguity in that passage, and physicists have been fighting about it for 87 years. There are at least 3 different English translations of the London and Bauer monograph in circulation, and they do not agree on the shading. One reading is strong. Consciousness physically breaks the chain. The mind reaches in and does something. Another reading is weaker and more careful. The observer's introspective knowledge is simply a different kind of information from anything else in the account, and once you have it, you are entitled to update your description in a way that no physical interaction licenses. Even on the weak reading, you have conceded something enormous, which is that the theory contains a step justified by a first-person fact and by nothing else. Either way, the terminus had a name now, and it was the worst possible name, because it is the one thing in the universe that physics has never been able to get a grip on. Therefore, somebody had to take it seriously at the highest level of the profession. And in 1961, that is exactly what happened, and it happened to be the man who had sat in the same Budapest classroom as von Neumann 5 years earlier. Eugene Wigner and John von Neumann met at the Fossori Lutheran Gymnasium as boys. They walked home together arguing about mathematics. Wigner said later, with the specific flatness of somebody stating an obvious fact, that he had known a great many brilliant people, and that only von Neumann's mind had made him feel he was in the presence of something different in kind. They went to Berlin together. They went to Princeton together. Wigner won the Nobel Prize in 1963 for the application of symmetry principles to atomic nuclei, and he is one of the reasons the modern conception of physical law is built around symmetry at all. In 1961, Wigner wrote an essay called Remarks on the Mind-Body Question for a collection edited by the statistician Irving John Good called The Scientist Speculates. It was reprinted in 1967 in his book Symmetries and Reflections, and half the internet now dates it to 1967, which is wrong, 1961. And in that essay, Wigner wrote the sentence that defined the next 60 years of argument. He wrote that it was not possible to formulate the laws of quantum mechanics in a fully consistent way without reference to the consciousness. A Nobel laureate. Not in a letter, not at a dinner party. In print, under his own name, in an essay he chose to reprint 6 years later. And his argument was not vague. It is the thought experiment that everybody now calls Wigner's friend, and it is worth doing carefully, because it is the exact moment the measurement problem stopped being an abstraction and became a scenario you can picture yourself standing in. You have a friend. Your friend is in a sealed laboratory. Inside that laboratory there is a quantum system in a superposition of 2 states, and your friend is going to measure it. From your friend's point of view, nothing strange happens. He runs the measurement, he sees a result, it is one thing or the other, he writes it in his notebook. His experience is completely ordinary. Now consider the situation from your point of view, standing outside the sealed laboratory. You have not interacted with the lab. Nothing has crossed the boundary. And quantum mechanics, applied honestly, tells you that the correct description of the contents of that room is a superposition, not of the particle, of your friend. Your friend having seen the first result and your friend having seen the second result, added together in a single quantum state, both present, neither realized. Wigner's response to this is one of the more human moments in the physics literature. He wrote that the situation appears absurd because it implies that his friend was in a state of suspended animation before he answered the question, and from that absurdity he concluded that the being with a consciousness must have a different role in quantum mechanics than the inanimate measuring device. The friend was conscious. Therefore, the friend's own awareness collapsed the state, from the inside, and the superposition Wigner would have written down was never correct in the first place. That is a real argument. It is not a stupid argument. It says that consciousness is the physical condition under which process 1 fires, and it explains in one move why you never see a smeared needle and why you have never met anybody who was in a superposition of moods. And it comes with a prediction, which is that the boundary of the quantum world sits at the boundary of awareness, wherever that is. And here is where it gets worse, because the moment you accept it, you inherit a set of questions that make the original problem look tidy. How conscious does the friend have to be? Wigner was aware of this and did not flinch from it, and asked in print about the difference between a friend and a dog and a molecule, and whether the collapse would be less complete for a less developed consciousness. Bell's sarcastic line about needing a system with a PhD is aimed directly at this. Where in evolutionary history did the universe acquire the ability to have definite facts in it? Was the wave function of the world genuinely waiting through 4 billion years of geology for the first nervous system? And more sharply than any of those, if consciousness is what collapses the wave function, and consciousness is a physical process in a brain, and brains are made of atoms that obey the Schrödinger equation, then consciousness is inside the chain, and the chain does not collapse itself. You have not escaped. You have just labelled the place where you stopped asking. Von Neumann had seen that. That is why he put the terminus outside the physical description entirely, in the subjective perception, rather than in the brain. He understood that any physical answer just extends the chain by one more link. Therefore, the consciousness answer only works if consciousness is not physical. Which is not a physics claim. It is a metaphysical bill, and Wigner, to his enormous credit, eventually looked at the bill and refused to pay it. That reversal is the single most underreported event in this entire history. Every popular account of quantum mechanics you have ever encountered will tell you that Wigner thought consciousness collapses the wave function. Almost none of them will tell you what he thought about it 20 years later. Wigner abandoned it, publicly, repeatedly, in his final decades. In a lecture in 1982, he said that his earlier position should be criticised as solipsism, which is about as brutal a thing as a physicist can say about his own past work. In 1984, he wrote that he had been converted out of it, and he named the person who converted him. A German physicist at Heidelberg called Heinz-Dieter Zeh, whose paper he had read. Leslie Ballantyne documented a public discussion in 1987 in which Wigner explicitly distanced himself from the claim that consciousness produces collapse. The most famous advocate of the idea that consciousness collapses the wave function spent the last decade of his life telling people he had been wrong about it, and the popular record simply did not absorb the correction. It is still, right now, the single most repeated claim about quantum mechanics on the internet, attributed to a man who publicly withdrew it, and I want to name what that does to the story, because it is not the tidy ending it looks like. Wigner did not withdraw because somebody found the flaw in his argument. Nobody found a flaw in his argument. He withdrew because a better mechanism appeared, one that seemed to make consciousness unnecessary, and he was intellectually honest enough to move, but the mechanism that convinced him does not do what he thought it did. He read Zeh's 1970 paper. He he saw that the environment destroys superpositions all by itself, with no minds involved anywhere, and he concluded the problem had been dissolved. It had not been dissolved. It had been relocated at enormous scale into a place where it is much harder to see. And Zeh himself, the man who wrote the paper, spent the rest of his life saying so. He is worth knowing about. Heinz Dieter Zeh, born the 8th of May 1932, the same year von Neumann's book appeared, did his doctoral work under Hans Jensen at Heidelberg in nuclear physics, in a completely conventional career. And in the late 1960s he started thinking about why large objects never show quantum behaviour, and he arrived at an answer so simple that its simplicity is the reason nobody had taken it seriously. No object is isolated. Ever, a dust grain floating in a sealed evacuated chamber is still being struck by photons. If you remove the photons, it is still sitting in the cosmic microwave background, the light left over from the origin of the universe, which fills every cubic centimetre of space, including the one you are in. If you could somehow shield the microwave background, the grain would still be exchanging gravitational influence with everything around it. Isolation is an idealization that does not exist anywhere in nature, and Zeh realized that this matters enormously, because quantum superposition is not a property an object has by itself. It is a property of the relationship between an object and everything it is correlated with. The moment a single photon bounces off your dust grain and carries away information about where the grain is, the grain is entangled with that photon. The superposition has not been destroyed, it has spread. And the interference effects that would tell you the superposition is there are now encoded in the correlation between the grain and a photon that is already halfway across the room and will shortly be halfway to Andromeda. Locally, the grain now looks classical. It looks like it is either here or there. The mathematics of the reduced description, the density matrix you get when you ignore the escaped photon, has lost its off-diagonal terms. That is decoherence. The word means what it says. The coherence between the branches, the thing that makes interference possible, has gone. Zeh wrote it up and sent it out, and the reception was bad. This part is not documented as cleanly as I would like, and I want to flag that rather than pretend otherwise. The paper was rejected repeatedly before it appeared. In 1970, in the first volume of a brand new journal called Foundations of Physics, pages 69 to 76, because established journals would not take it. Zeh said afterwards that he was warned this line of work would end his career. What is documented very clearly is what he told his own student. When Eric Jews began working with him, Zeh instructed him to steer clear of any reference to interpretation, and to avoid mentioning Everett by name, and to concentrate purely on the consequences for the reduced density matrix. Zeh's own explanation of why. This was something nobody could deny. Think about what that sentence describes. A physicist coaching a graduate student on how to smuggle a correct idea past the profession by stripping out everything that makes it matter. Not because the idea was wrong, because the implication was unemployable. Zeh died on the 15th of April, 2018. By then, decoherence had become one of the most cited concepts in physics, and every quantum computing group on Earth spends its entire research budget fighting the effect he described, and the standard undergraduate account of what he discovered says he solved the measurement problem. He did not think he had solved the measurement problem. He said so for 48 years. Because here is what actually happens when you follow the decoherence story to the end, and this is the part that took me longest to get straight in my own head, and it is the exact place where the second layer of this whole thing opens up underneath the first. Decoherence does not collapse anything. Nothing collapses. Not the grain, not the photon, not the detector. What decoherence describes is a superposition getting bigger. The grain and the photon are now in a joint superposition. The photon hits the wall, and the wall joins in. The wall warms by an unmeasurable fraction and radiates, and the room joins in. the whole thing propagates outward at the speed of light, and every atom it touches becomes part of the same entangled state, and nowhere in that process does the universe ever choose. Zay understood this from the beginning. His view was explicitly Everettian. The branches are all still there, all of them, permanently, and Decoherence explains why the branches stop being able to talk to each other, which is why you never see interference between a world where the needle went left and a world where it went right. That is a real explanation of a real thing. It is one of the genuine achievements of 20th century physics. It is not an explanation of why you see one needle. Von Neumann's chain did not get cut, it got wider. Instead of running from the particle through the apparatus to your retina, it now runs from the particle through the apparatus, through the air, through the walls, through the atmosphere, through the escaping infrared into deep space, expanding at 300,000 kilometers per second, and it has been doing that continuously since before you were born. The cut is still nowhere. It is just further away now, and moving. And I want to be honest that when I first properly understood that, my reaction was to assume I had misunderstood something, because it cannot be true that the standard modern answer to the measurement problem does not answer the measurement problem. That is not a thing that can be quietly true in a mature science with 100,000 practitioners. It is quietly true, and the people who built Decoherence have been saying so in print, in the highest impact journals in physics, for 40 years, in sentences of unmistakable clarity that essentially nobody outside the Foundation's community has ever read. We are going to read them. But first the numbers, because the numbers are the reason Decoherence won, and they are genuinely spectacular. Eric Jews and Zare published the calculation in 1985 in Zeitschrift für Physik B, volume 59, pages 223 to 243. They took a dust grain, a real one, a sphere about 10 microns across, and they asked how long a superposition of that grain being in two different places would survive under various conditions. In ordinary air at normal pressure, the interference is gone in about 10 to the minus 31 seconds. I need to stop on that, because a number like that goes past you without touching anything. 10 to the minus 31 seconds is a decimal point, followed by 30 zeros, and then a 1. Here is the comparison that made it land for me. The age of the universe is roughly 10 to the 18 seconds, which means 10 to the minus 31 seconds is to 1 second, as 1 second is to a period of time 30 trillion times longer than the entire history of the universe since the beginning. That is the window in which a speck of dust in this room is allowed to be in two places at once. In a good laboratory vacuum, the best you can make, the number improves to about 10 to the minus 27 seconds. Still hopeless. Now take the grain into interstellar space, where there is no air, no dust, and effectively nothing at all. What is left is the cosmic microwave background, the faint bath of radiation at 2.7 Kelvin left over from the early universe, which is the emptiest condition physically available anywhere. And the answer Jews and Zay got is that the microwave background alone decoheres the grain in about 1 second. 1 second. The coldest, emptiest place that exists in the universe still contains enough light to destroy the quantum behavior of a dust particle in the time it takes you to exhale. This is why nobody has ever seen a superposed cat. Not because it is impossible in principle, because the environment is a measuring device that never stops measuring, at a rate that makes the entire history of biology look instantaneous by comparison. Wojciech Zurek at Los Alamos took Zay's insight and turned it into a quantitative program through the 1980s. 2 papers in Physical Review D did most of the work. Volume 24, page 1516, 1981, titled Pointer Basis of Quantum Apparatus, and Volume 26, page 1862, 1982, on environment-induced superselection, and his review article in Reviews of Modern Physics, Volume 75, page 715, in 2003. is one of the most cited papers in the foundations of physics. Zurich's edition solved a problem that had been sitting there since the 1930s and that almost nobody even notices is a problem. When a superposition collapses, why does it collapse into these particular options and not others? A needle can point left or right, but the mathematics also allows a state that is the sum of pointing left and pointing right, and there is nothing in the collapse postulate itself that says which set of alternatives is the real one. Zurich showed that the environment picks. The states that survive being constantly monitored by the environment are the ones that do not get scrambled by that monitoring. And for macroscopic objects, those states are localized in position. He called the process inselection, environment-induced superselection. It is why the classical world is made of things that have positions, rather than things that have definite momenta or definite anything else. That is a genuine, deep, correct piece of physics. It explains the shape of the classical world. And it was tested. This is not theory that sits in journals. Marcus Arndt and Anton Zeilinger's group in Vienna ran the experiment in 1999 and published it in Nature, volume 401, pages 680 to 682. They took carbon-60, Buckminster fullerene, a molecule of 60 carbon atoms shaped like a football, with a mass of 720 atomic mass units and a diameter of about 1 nanometer, heated it in an oven to 900 Kelvin until it sublimated, and sent the molecules one at a time through a grating made of silicon nitride with slits 50 nanometers wide, and they got an interference pattern. A molecule containing 60 carbon nuclei and 360 electrons. An object roughly 350 times larger than its own de Broglie wavelength, went through multiple slits simultaneously. Then, and this is the experiment that actually matters for our story, they did the reverse. In 2004, Lucia Hackemuller and colleagues published a paper in Nature, volume 427, pages 711 to 714, in which they took the same interference pattern and deliberately destroyed it. They heated the molecules. A hot molecule radiates thermal photons. Each photon carries away a little information about where the molecule is, and as they raise the temperature, the fringe visibility died. Exactly on the curve the decoherence theory predicted, with no observer involved and nothing conscious anywhere in the building. That is as clean as experimental physics gets. They turned decoherence into a dial and watched the quantum world become classical as they turned it. And they kept going. In 2019, Yakov Fine and colleagues in the same Vienna lineage published in Nature Physics, volume 15, pages 1242 to 1245, an interference experiment with tailored molecules called oligoporphyrins with masses beyond 25,000 atomic mass units. Some of these things contain around 2,000 atoms. One of them, and I am going to read the formula because the absurdity is the point, has 707 carbon atoms, 260 hydrogens, 908 fluorines, 16 nitrogens, 53 sulfurs and 4 zinc atoms, adding up to more than 40,000 protons, neutrons and electrons. It was passed through a 2-meter-long interferometer. Its de Broglie wavelength was around 53 femtometers, which is smaller than the diameter of the molecule by a factor of about 1,000, and it interfered with itself at more than 90% of the theoretically expected visibility. Objects containing 2,000 atoms are in 2 places at once, in Vienna on a regular basis, and it is engineering now. Therefore, decoherence is real, quantitative, tested, and one of the best confirmed pieces of physics we have. And every single word of that is compatible with the measurement problem being exactly as unsolved as von Neumann left it. And this is the point in the story where the people who built the field start saying so out loud. Stephen Adler is a theoretical physicist at the Institute for Advanced Study in Princeton, the same institution where von Neumann spent his career. In 2003 he published a paper in Studies in History and Philosophy of Modern Physics, volume 34b, pages 135 to 142, and the title is not subtle. why decoherence has not solved the measurement problem. It is a response to Philip Anderson, a Nobel laureate, who had claimed in print that decoherence had disposed of the whole business. Adler's opening sentence is this: "It has lately become fashionable to claim that decoherence has solved the quantum measurement problem by eliminating the necessity for von Neumann's wave function collapse postulate." Fashionable? He chose that word deliberately, and it is the most withering word available in that register, because it says the belief is being held socially rather than argued for, and his argument is the one Zeh had been making for 30 years, stated with total precision. Decoherence is derived by taking a system entangled with an environment and tracing out the environment, discarding the information you cannot access, and looking at what is left. What you get is a mathematical object that looks exactly like a classical statistical mixture. It looks like the needle is either left or right with such and such probabilities. But looking like a mixture and being a mixture are not the same thing, and the reason they are not the same thing is that the global state, the one that includes everything you traced out, is still a pure entangled superposition, and always will be. The mixture is a description of your ignorance. Nothing in the physics has selected an outcome. You have simply agreed to stop looking at the part of the universe where the other branch is still sitting. Maximilian Schlosshauer, whose review in Reviews of Modern Physics, volume 76, pages 1267 to 1305, in 2005, is the standard reference on the entire subject, states the same limitation as the consensus position of the field. Decoherence explains the absence of interference. It does not explain the occurrence of a definite outcome. Zurich's own review says it. Zeh said it from the first paper onward. Every architect of the theory that supposedly solved the measurement problem has written down, in print, that it does not solve the measurement problem. And here is where I get genuinely angry, and I have thought about whether that is a fair reaction, and I have decided that it is. This is not an obscure technical dispute buried in a specialist literature. This is the central interpretive question of the most successful theory in science, and the answer to it that has been transmitted to the educated public, in textbooks, in popular books. In undergraduate courses, in every documentary you have ever seen, is a claim that the people who built the relevant physics explicitly deny in writing, not in private. In Reviews of Modern Physics. The mechanism is not conspiracy. It is much more ordinary than that, and much harder to fix. Decoherence gives working physicists everything they actually need. It tells them when quantum effects will be visible, and when they will not, which is the only question that matters if you are building a qubit, or a sensor, or a laser. The remaining question, the one about why there is a fact of the matter at all, is not a question you can get funded to work on, does not appear on any exam, and has no experimental consequence that anyone has yet been able to devise. And a question with no experimental consequence, in a professional community organised entirely around experimental consequence, does not get called unsolved. It gets called philosophy, and the word philosophy in a physics department is not a compliment. That is how a hole this size stays open for 94 years without anybody lying about anything. And still we have not reached the bottom. Because the obvious response to everything I have just said is that the interpretations exist for a reason, that serious people have built serious alternatives, and that one of them presumably works. They do exist. Some of them are magnificent, and every single one of them pays a price that the person selling it to you tends not to mention. Start with the one that takes von Neumann completely literally. Hugh Everett III was born on the 11th of November, 1930, and arrived at Princeton in the mid-1950s as a graduate student working under John Archibald Wheeler. He looked at process 1, the collapse postulate, and he asked the question that a certain kind of mind cannot help asking. What if you just deleted it? What if the wave function is all there is, and it never collapses, and process 2 is the entire content of physics? The answer is that you get everything right except your own experience, and then you get that right too, but at a cost. If there is no collapse, then when your friend measures the particle, the friend genuinely does end up in a superposition of having seen both outcomes. There is a version of the friend who saw the first result, and a version who saw the second, and both are equally real. And neither of them can ever detect the other, because decoherence has severed the connection between them. Each version is a complete person with a complete memory, and each of them believes that a collapse occurred. Everett called it the relative state formulation. It was Bryce DeWitt who later gave it the name that stuck, which is many worlds, and which Everett himself never used. The mathematics is astonishingly economical. You remove an axiom. That is the entire proposal. There are no new equations, no new constants, no new physics of any kind, and the measurement problem dissolves, because there was never a single outcome to explain in the first place. And what it costs you is probability. This is the part that gets skipped in every popular account, and it is fatal or nearly fatal depending on who you ask. Quantum mechanics does not just say that outcomes happen. It says they happen with specific frequencies, given by the square of the amplitude, the Bohm rule, and that rule has been confirmed to extraordinary precision for a century. But if every outcome happens, and there is a version of you for each one, then in what sense is one outcome more probable than another? Both of them occurred. There is one of you in each branch. Counting branches gives you the wrong answer. David Deutsch in 1999 and David Wallace afterwards developed a genuinely ingenious derivation using decision theory, arguing that a rational agent in a branching universe would be forced to bet as if the Bohm rule held. It is beautiful work. It is also, and this criticism has never gone away, arguably circular, because the rationality axioms it uses have to be chosen, and the critics say they smuggle in the very measure they are supposed to derive. Everett presented his work, and it went nowhere. Wheeler, trying to protect him, forced him to cut the thesis down to a fraction of its length before publication, removing most of the argument, and sent him to Copenhagen in the spring of 1959 to talk to Bohr in person. The meeting was a disaster. Everett could not make himself understood, and Bohr's circle regarded the whole thing as a young man who had failed to grasp the point. The short version appeared in Reviews of Modern Physics, Volume 29, pages 454 to 462 in 1957, and was almost entirely ignored. The full thesis was not published until 1973. By then, Everett was not a physicist. He had left the field completely and gone into weapons analysis, working for the Weapons Systems Evaluation Group, where he co-authored a document called Report Number 50 on the effects of nuclear war, which is still classified in part, and which was foundational to American thinking about mutually assured destruction. A man who could not persuade the physics establishment that unobserved branches of reality were real spent the rest of his working life calculating, in detail, the outcomes of a war that has never happened. He drank heavily. He smoked constantly. He was, by his family's account, emotionally absent in a way that his son has described publicly and at length, because his son is the musician Mark Oliver Everett, who found his father's body. Everett died in his sleep on the 19th of July, 1982, at the age of 51. 14 years later, his daughter Elizabeth took her own life, and left a note saying that she was going to join her father in another universe. I am not going to make that into a neat piece of irony. It is not ironic. It is just a family destroyed around an idea, and the idea turned out to be one of the 2 or 3 most seriously held positions in modern physics, and he did not live to see any of it. Therefore, Many Worlds keeps the physics intact, and pays in probability and in an infinity of unobservable branches. The other great alternative pays somewhere else entirely. David Bohm took the opposite route. Rather than deleting the collapse, he added the thing von Neumann had supposedly proved impossible: hidden variables. In 1952 in Physical Review, Volume 85, In 2 consecutive papers starting at page 166 and page 180, he wrote down a theory in which particles always have definite positions, always at every moment, and are guided along their trajectories by the wave function acting as a physical field. There is no collapse and no measurement problem, because there was never any ambiguity about where anything was. The apparent randomness comes entirely from your ignorance of the initial positions. It works. It reproduces every prediction of standard quantum mechanics exactly. It was the living refutation of von Neumann's impossibility theorem, published 14 years before Bell explained why the theorem failed, and its existence should have detonated the consensus on its own. The price is non-locality. In Bohm's theory, the velocity of any particle depends instantaneously on the positions of every other particle in the system, no matter how far apart they are, not as an approximation. As a structural feature, the theory is explicitly, unashamedly, faster than light in its inner workings, and it survives only because that influence cannot be used to send a signal. And what happened to Bohm is the second entry in a pattern that by this point in the story has stopped looking like coincidence. He was born on the 20th of December, 1917, in Wilkes-Barre, Pennsylvania. He did his doctorate under Oppenheimer at Berkeley, and in 1949 he was subpoenaed by the House Un-American Activities Committee, refused to testify against colleagues, invoked the Fifth Amendment, and was arrested in December 1950 for contempt of Congress. He was acquitted on the 31st of May, 1951. Princeton suspended him from teaching anyway, and declined to renew his contract, and Einstein, who wanted him as an assistant, could not get the decision reversed. Bohm left for Sao Paulo, and when he arrived in Brazil, the American consulate confiscated his passport, which meant he could not leave. He wrote the 1952 papers in exile, holding a document that would not let him travel, in a country whose language he did not speak, and the reception in Copenhagen and Princeton was not that he was wrong. Nobody could show he was wrong. The reception was that the work was pointless, a step backwards, uninteresting. Bohm eventually reached Birkbeck College in London, was elected a Fellow of the Royal Society in 1990, and died in 1992. Count them. Hermann catches the floor in 1935 and is ignored for 4 decades. Bohm builds the working counterexample in 1952 and is exiled. Everett removes the offending axiom in 1957 and leaves physics entirely. Zeh explains why the classical world looks classical in 1970 and is told it will finish his career. Bell demolishes the wall in 1966 and spends the rest of his life doing this work in his spare time because CERN paid him to design accelerators. 5 people across 35 years, all of whom turned out to be correct about the specific technical thing they said, all of whom were professionally penalized for saying it. That is not a conspiracy, and there is no committee anywhere that met about it. It is something more banal and much more durable, which is that a field develops a shared sense of which questions are serious, and that sense is enforced socially through hiring and refereeing and what gets treated as a real seminar topic. And it takes generations to move. But suppose you do not want branches and you do not want non-locality. There is a third option, and it is the only one that makes the whole thing an experimental question rather than a philosophical one, which is why the last 20 years of this story belong to it. The idea is that process 1 is real. Collapse actually physically happens. It is not an artifact of anything, and the reason we cannot find it in the equations is that our equations are wrong. Quantum mechanics is an approximation to a deeper theory in which the wave function occasionally, spontaneously, without any observer or environment or measurement, localises by itself. The first serious version came in 1986 from Giancarlo Girardi, Alberto Rimini, and Tullio Weber, published in Physical Review D, volume 34, page 470. Their proposal, universally called grrr, is that every particle in the universe has a tiny probability per unit time of undergoing a spontaneous spatial localization. The rate they proposed is around 10 to the minus 16 per second per nucleon, and the width of the localization is about 10 to the minus 7 meters. Work out what that means, and the elegance is remarkable. For a single particle, 10 to the minus 16 per second means one collapse every 10 to the 16 seconds, which is roughly 300 million years. An isolated electron essentially never collapses, which is why quantum mechanics works perfectly in the laboratory. But a macroscopic object contains something like 10 to the 23 nucleons, and they are all entangled with each other, so a collapse of any one of them drags the whole object with it. 10 to the 23 particles, at 10 to the minus 16 collapses per second, each gives you around 10 million collapses per second for the object as a whole. A dust grain cannot stay in superposition for more than a fraction of a microsecond. A cat is localized before any part of it could ever become ambiguous. One set of numbers, and both the quantum behavior of particles and the classical behavior of cats fall out. There is no cut anywhere. There is no observer anywhere. Von Neumann's chain is severed by a law of nature at a rate that scales with size. The cost is that these are new constants of nature, invented to solve a problem with no independent justification. And the theory only counts as physics if those constants can be measured, which means the whole approach lives or dies on experiment. And that is where Roger Penrose comes in, with the most beautiful version of the idea anyone has proposed, and the one that got killed. Penrose's argument, developed through the 1990s and anticipated independently by the Hungarian physicist Lajos Diossi in 1987, starts from a genuine conflict between the two great theories of the 20th century, and it is a conflict that most physicists prefer not to look at directly. Quantum mechanics says a massive object can be in a superposition of two positions. General relativity says a massive object curves space-time around it. Put those two statements next to each other and ask the obvious question. If the object is in two places, what is space-time doing? There is no consistent answer within either theory. You end up with a superposition of two different space-time geometries, and general relativity has no framework for that. Because in general relativity, the geometry is what defines what simultaneity and duration even mean. You cannot superpose two definitions of time without the notion of time itself becoming ambiguous. Penrose's proposal is that nature refuses, that a superposition of two mass distributions is unstable, and that it decays on a timescale set by the gravitational self-energy of the difference between the two configurations. Take the two mass distributions, compute the gravitational energy of the difference, call it E, and the superposition lasts about Planck's constant divided by that energy. For an electron, that time is astronomically long. For a cat, it is far shorter than any biological process. The transition from quantum to classical is set by gravity, requires no observer, and involves no new constants at all, because the only quantity in the formula is Newton's gravitational constant, which we already have. That is the most attractive proposal in this entire field. It solves the measurement problem, it explains the quantum to classical transition, it uses no free parameters, and it predicts that the collapse is a real physical event with real physical consequences. I remember reading Penrose's version of this properly for the first time and thinking that it was too good not to be true. And in 2020, a group of physicists went into a mountain and killed it. The logic of the test is subtle, and I want to get it right. If the wave function of a charged particle is being spontaneously and randomly localized by gravity, then the particle is being jostled. Localization in position means a spread in momentum, which means the particle is picking up tiny random kicks, continuously, from nothing. And a charged particle that is being accelerated radiates, which means that if this model is correct, all ordinary matter, everything, every atom in your body, and every atom in this room, must be very faintly glowing with spontaneously emitted radiation that has no source. That radiation is far too weak to see against the ordinary background of the world. Cosmic rays alone would swamp it by many orders of magnitude, which means you go somewhere with no background. Sandro Donardi, Christian Pasiccia, Catalina Curcianu, Lajos Diosi himself, Matthias Laubenstein, and Angelo Bassi ran the experiment at the Gran Sasso National Laboratory in Italy, which sits under about 1,400 meters of rock in the Apennines, shielded from cosmic radiation by the mountain above it. They used a high-purity germanium detector, itself shielded further, and they looked for the faint X-ray and gamma-ray emission that the model requires. The result was published in Nature Physics, Volume 16, pages 1008 to 1011, in 2020. They found nothing, no excess emission at all, at a sensitivity roughly 1,000 times better than any previous bound. And the paper says, in the plainest language a nature physics paper is capable of, that this rules out the natural parameter-free version of the Diosy-Penrose model. In the body of the text they put it even more starkly, that Penrose's proposal for a gravity-related collapse of the wave function, in its present formulation, is ruled out. Think about what that actually means, because it is one of the strangest sentences in modern experimental physics. A group of scientists went 1.5 kilometers underground, inside a mountain, to test whether reality has a mechanism for deciding what is real, and the answer came back no. Not this mechanism. The broader family survives, in modified forms with extra parameters bolted on, and the same collaboration has continued to squeeze the spontaneous collapse models with further results through 2024. Every year the allowed region of parameter space gets smaller. Every year the theories have to be adjusted to fit into what is left. That is what a theory looks like while it is being falsified. Therefore, we have arrived at the current state of play, and it deserves to be stated bluntly. The consciousness answer was abandoned by its own champion. The decoherence answer explicitly does not answer the question, and its architects say so. Many worlds keeps the mathematics clean at the cost of probability, meaning anything. Pilot wave keeps definite outcomes at the cost of a hidden layer of superluminal influence. Spontaneous collapse makes it an experimental question, and the experiments have started coming back negative, and into that situation, in 2018, walked 2 theorists from Zurich with a thought experiment that made everything worse. Daniela Fruchiger and Renato Renner published a paper in Nature Communications, Volume 9, Article 3711, and the title alone is a provocation. Quantum theory cannot consistently describe the use of itself. What they did was take Wigner's friend and iterate it. 2 sealed laboratories, each containing a friend, and 2 outside observers, each of whom treats a laboratory and its occupant as a quantum system and applies the standard formalism to it. All 4 agents use quantum mechanics. All 4 reason correctly. All 4 are allowed to use each other's conclusions, which is something scientists do constantly and which nobody thinks is controversial. And in one particular branch of the experiment, which occurs with probability 1 in 12, the agents reach contradictory certainties. One of them concludes with certainty that the outcome must be a particular result. Another concludes with equal certainty that it must be the other. They are both applying quantum mechanics correctly. They are both right. Fruchiger and Renner extracted the 3 assumptions that produce the contradiction and showed that you cannot keep all of them. First, that quantum theory applies universally, including to observers and laboratories. Second, that agents can consistently adopt each other's conclusions when they reason correctly. Third, that a measurement has a single outcome. Pick one to abandon. Many worlds abandons the third and says there is no single outcome. Copenhagen style views abandon the first and say the theory does not apply to observers. Relational and Bayesian views abandon the second and say that different agents genuinely have different facts. There is no fourth option and no free lunch, and the paper does not tell you which to choose, it just closes the exits. The paper is heavily criticised, and I should say so honestly. Anthony Sudbury published a careful analysis of the hidden assumptions. Dustin Lazarovici and Mario Hubert published a rebuttal in Scientific Reports arguing that quantum mechanics can consistently describe the use of itself if you are careful about what the agents actually know. Aurélien Drezet responded from the Bohmian side. The argument continues, but even the critics agree on what the paper achieved, which is that it forced every interpretation to declare, in public, which piece of ordinary reasoning it is willing to sacrifice. And then people started building it. In 2019, a group at Heriot-Watt University in Edinburgh, led by Massimiliano Proietti with Alessandro Fedrizzi, published an experiment in Science Advances, Volume 5, article number EOR 9832, titled Experimental Test of Local Observer Independence. They built a version of the extended Wigner's friend scenario using 6 photons, arranged in 3 entangled pairs, implementing 4 observers. 2 of the photons played the role of the friends inside the sealed laboratories, and 2 played the role of the outside observers who measure the whole laboratory. Then they tested a Bell-type inequality derived specifically for this scenario, one which holds if you assume that the events observed by the friends are absolute facts, and that the outside observers cannot influence them faster than light. The inequality was violated by more than 5 standard deviations. Their conclusion in the paper is that if you hold on to locality and free choice of measurement settings, then quantum theory has to be interpreted in an observer-dependent way. The facts recorded by the friend inside the lab and the facts recorded by the observer outside the lab cannot both be absolute. Now I have to give you the caveat, because this audience will find it anyway, and because the honest version is more interesting than the hyped version. The observers in that experiment were photons. There is nothing conscious in the apparatus, nothing that has an experience, nothing that could be said to know anything. The photon path plays the formal role of a measurement record. What the experiment demonstrates is that the logical structure of the paradox is physically realizable, that the mathematics is not a trick of the thought experiment, and that no local model in which the friend's record is an absolute fact can reproduce what the laboratory measures. That is a real and serious result, and it is not the same as showing that 2 people disagreed about what happened. Anyone telling you that a photon was confused about reality is selling something. The following year, the theoretical machinery got much sharper. Kokwé Bong, Aníbal Utreras Alarcón, Eric Cavalcanti, Howard Wiseman and colleagues at Griffith University in Australia published in Nature Physics, Volume 16, pages 1199 to 1205. A paper called A Strong No-Go Theorem on the Wigner's Friend Paradox. Their theorem, which they call local friendliness, isolates the assumptions with a precision that Bell's original theorem does not have. There are 3. Local agency, which says that a freely chosen measurement setting has no influence on distant events outside its future light cone. No superdeterminism, which says the settings can be chosen freely in the first place. And a third assumption that they named, and the name is the sharpest thing in the paper. Absoluteness of observed events. The claim that an observed event is an absolute fact about the world, not a fact relative to anybody. The 3 cannot all be true, and they proved that the resulting constraint on physical reality is strictly stronger than the one Bell derived in 1964, which means this is not a rephrasing of an old result. It is a new and tighter box. Absoluteness of observed events. Somebody had to write that down as an assumption, formally, in a Nature journal, because it turned out that it might not be true. The idea that when something happens, it happens, full stop for everybody, is now a technical premise in a no-go theorem, and it is one of the premises that has to go. Which brings us to the interpretations that took the hint and made observer relativity into the foundation, rather than the scandal. There are 2 serious ones. QBism, developed by Christopher Fuchs, David Mermin and Rudiger Schack, says that the quantum state was never a description of the world at all. It is an agent's personal degree of belief about what she will experience if she acts. Collapse is not a physical process, it is what happens to your beliefs when you learn something. and it is no more mysterious than updating a probability when you look at a card. Measurement outcomes are personal experiences, full stop. Relational quantum mechanics, developed by Carlo Rovelli, takes a similar move but frames it physically rather than psychologically. There are no observer-independent states and no observer-independent facts. Every fact is a fact relative to some physical system. When the detector interacts with the particle, an outcome exists relative to the detector. It does not yet exist relative to you. Both of these dissolve the measurement problem completely, and I want to be fair to them, because they are the work of extremely serious people and they are internally consistent. Von Neumann's chain simply does not arise. There is no puzzle about where the cut goes, because the cut is wherever the agent is, by definition, and asking for its objective location is a category error. The price is the thing you have to hand over to get it, and the price is enormous. You have to give up the single shared world of events, not the deterministic universe, not locality. Those were already gone. The thing you have to abandon is the assumption that there is one history, one set of things that happened, the same for everybody, which every human being who has ever lived has taken as the background condition of existence. In these views, your outcome is real for you. The friend's outcome is real for the friend. There is no third-person account in which both are simultaneously and objectively the case, and the question of what really happened, unrelativized, is not an unanswered question, it is a malformed one. And now the consensus flip, and this is the part I did not expect when I started reading for this. You would assume, given a century of argument, that the profession has quietly converged on something. It has not. In July 2011, at a conference in Traunkirchen in Austria on quantum physics and the nature of reality, Maximilian Schlosshauer, Johannes Koffler, and Anton Zeilinger handed out a questionnaire. 35 people attended. 33 completed it. They published the results in Studies in History and Philosophy of Modern Physics, Volume 44, pages 222 to 230. Favourite interpretation: Copenhagen, 42%. Information-based views, 24%. Everett and many worlds, 18%. Objective collapse, 9%. QBism, 6%. De Broglie-Bohm, 00. Not a single one of the 33 physicists in that room chose the one interpretation that is fully worked out, mathematically explicit, and demonstrably capable of reproducing quantum mechanics without any collapse or branching at all. 2 years later, Travis Norson and Sarah Nelson ran the same style of poll at a conference in Bielefeld, with 76 respondents. De Broglie-Bohm, 63%. Copenhagen, 4%. The same question, the same year range. Opposite answers, because a different set of people happened to be in the room. That is not a science that has converged. That is a science that has developed tribes. In 2016, an online poll by Sujeevan Sivasundaram and Christian Nielsen went out to 1,234 physicists across 8 universities and got 149 responses. Copenhagen led with 39%, and the second largest group, at 36%, said they had no preferred interpretation at all. Which is its own kind of answer, and last year, in the centenary of quantum mechanics, a further poll published in Foundations of Physics found Copenhagen at 60%, de Broglie-Bohm at 23%, Everett at 7%. 100 years, no convergence. And the most popular answer throughout is the one that Bell spent his career attacking as an instruction manual rather than a theory, and that Adler called fashionable, and that most of the people who select it in a poll will tell you privately means nothing more than shut up and calculate. But there is one number in that 2011 poll that matters more than the interpretation counts, and it is the number that closes the loop back to von Neumann. 55% of the respondents endorsed the statement that the observer plays a fundamental role in the application of the formalism, but plays no distinguished physical role. Read that carefully, because it is a very carefully built sentence, and it is doing something remarkable. It says the observer is essential. You cannot write the theory down without one. The formalism requires an agent to whom outcomes occur, and in the same breath it says that this observer is not a physical thing, has no physical properties, exerts no physical influence, and appears nowhere in the dynamics. That is not a resolution of von Neumann's chain. That is the majority of a room full of expert physicists formally agreeing to the exact structure that von Neumann described in 1932 and declining to say what it is. The terminus is required. The terminus is not physical. Nobody knows what it is. 55% on the record at a conference, in a peer-reviewed journal. There is a misconception I have been holding back until now, because correcting it early would have let you off the hook, and I want to do it here, where it lands properly. If you have picked up anything about quantum mechanics from popular sources, you have absorbed the idea that the observer in quantum mechanics means a conscious human being. That is the version everyone knows, and it is the version that the entire quantum mysticism industry is built on. And it is wrong. It is wrong in the textbooks, it is wrong in the axioms, it is wrong in the working practice of every physicist alive. 55% of that Vienna room said so explicitly. The observer in quantum mechanics is not required to be conscious, and a Geiger counter. A photographic plate, a cloud chamber and a bubble of gas will all do the job. Good. Now here is what that correction actually costs you, and it costs more than the mistake did. If the observer need not be conscious, then what is it? Go and look. Take the actual axioms of quantum mechanics, in the actual books that physicists learn from, and try to find a definition of measurement. Dirac's Principles of Quantum Mechanics, the founding textbook, treats measurement as a primitive act and never defines it. Von Neumann's own book states the projection postulate as a postulate, which is to say a thing assumed rather than derived, applying under conditions the book does not specify. Sakurai's Modern Quantum Mechanics, which is the standard graduate text in the English-speaking world, presents the measurement postulate as a rule about what happens when a measurement occurs, and defines the word nowhere. Griffiths, which is what every undergraduate physicist in the world learns from, does the same. Nielsen and Chuang, the Bible of Quantum Computing, lists measurement as one of the postulates in Chapter 2 and describes the mathematics of it in complete detail without ever saying what physical process qualifies. 5 books, millions of students, 94 years. The central term is undefined in all of them. This is what Bell was attacking in 1990 when he wrote against measurement. His argument was not that physicists get the wrong answers. They get the right answers to 11 decimal places. His argument was that a fundamental theory of nature cannot contain, in its axioms, a term that refers to a vague human activity, and that the word measurement should be banned from the foundations of physics entirely, along with apparatus, environment, macroscopic, observable, and information. He called them unprofessional. He said the theory was unprofessionally vague and ambiguous, and nothing has changed since he wrote it. Now I owe you the strongest version of the opposing case, because I have been building an argument for 2 hours, and if I do not steelman the other side, you should not trust me. The pragmatist position goes like this, and it is held by extremely capable people. Quantum mechanics is a formalism for predicting the statistics of measurement outcomes. That is what it is for. It does this flawlessly. The demand that it also tell you what is happening when nobody is measuring is a demand from metaphysics, not from physics. And it is a demand that no theory has ever satisfied, and none is obliged to satisfy. Newton was attacked for the same thing. He described gravity as action at a distance with no mechanism, and was told repeatedly that this was occult nonsense, and his answer was that he framed no hypotheses, and he was right, and the mechanism turned up 230 years later when Einstein arrived. Theories describe. Understanding is optional and usually late. On top of that, the pragmatist says, look at what the word problem is doing in the phrase measurement problem. A problem is something that obstructs you. This one obstructs nothing. Not a single experiment in 100 years has come out differently because of it. Not one piece of technology has failed. There is no calculation anywhere that anybody cannot do. Whatever this is, it is not a scientific problem in the sense that the anomalous perihelion of Mercury was a scientific problem, because Mercury's orbit was actually wrong and this is not wrong about anything. That is a serious case. I think it is wrong, and I want to say exactly where, because the place it fails is precise. It fails because quantum mechanics is not offered as a theory of laboratories. It is offered as a theory of everything that is made of matter, which is everything. Cosmologists apply it to the entire universe, to the fluctuations in the early cosmos that seeded every galaxy that exists, including the one you are in. There were no observers then. There were no laboratories, no apparatus, no measurements, and no people, and the theory is nevertheless applied to that period, and the predictions come out right, which is one of the great achievements of modern science. But if the formalism is only a recipe for the statistics of measurement outcomes, and there were no measurements, then what exactly is being predicted? Either the theory describes what actually happened in the absence of anybody, in which case it needs an account of how things happen, or it does not, in which case the fluctuation pattern in the cosmic microwave background is a statement about our expectations rather than about the early universe, and I do not think most cosmologists would sign that. You cannot have both. You cannot claim the theory is merely an instrument for organizing human experience, and also claim it tells you what the universe did before there were humans. Pick one, and there is a second failure that is closer to home. The pragmatist argument assumes the problem has no experimental consequence, and that assumption used to be true and is no longer true. Spontaneous collapse models are physics. They make different predictions from standard quantum mechanics. They are being tested in mountains right now, and one of them has already been killed. The local friendliness theorem produces an inequality you can violate in a laboratory, and it was violated. Whether reality contains absolute facts has become an experimental question with published data attached to it. The moment that happened, the pragmatist defense stopped being a philosophical position and became a bet on the outcome of ongoing experiments. That is a perfectly respectable thing to be. It is not a reason to stop asking. And I will say the harder thing too, because I think it is true. The shut up and calculate posture was never really an epistemological argument. It was a professional survival strategy that hardened into a virtue. It grew in a specific period, in the 1940s and 50s, in an American physics culture reorganized around weapons and industry and rapid results, where the men who kept asking the awkward questions were the men who got exiled and unemployed and quietly moved out of the field. Hermann, Bohm, Everett, Zare. The generation that learned to call the question meaningless was the generation that watched what happened to the people who did not. That is not a conspiracy, and it does not require anybody to have acted in bad faith. It only requires that a discipline, like any human institution, learns which questions are safe. Now think about what has been built on top of that undefined term while nobody was looking. There are companies right now with valuations in the billions whose entire business is the manipulation of quantum superposition. Every quantum computing effort on Earth, in Santa Barbara and Zurich and Hefei and Delft, is engaged in a war against decoherence, spending hundreds of millions of dollars keeping objects in superposition for microseconds, longer than they otherwise would be. Dilution refrigerators running at 10 millikelvin, which is colder than any naturally occurring place in the known universe. Colder than interstellar space by a factor of nearly 300, built for no reason other than to hold back the environment from measuring the qubit. Every one of those machines is a device for controlling exactly where von Neumann's cut falls. That is literally the engineering problem. You are trying to keep the chain from propagating out of your processor and into the world for long enough to finish a calculation, and the moment it escapes, your computation is destroyed. The entire industry is applied measurement problem, and not one person in it can tell you what a measurement is. And when the calculation ends, you read the result out, and something in that readout produces one number rather than a superposition of numbers, and nobody knows what that step is either. I find that genuinely difficult to hold in my head. We have industrialized a process we cannot define. But the deepest thing in this story is not the industry, and it is not the textbooks. It is the pattern you get when you line all the interpretations up next to each other and look at what they share, because they disagree about literally everything else. Copenhagen says the wave function is not real, and there is no point asking what happens between measurements. Many Worlds says the wave function is the only real thing, and all outcomes occur. Pilot Wave says the wave function is real, and so are the particles, and the particles always had positions. Spontaneous Collapse says the wave function is real, and it breaks by itself according to a law we have not found. QBism says the wave function is a state of belief inside an agent. Relational quantum mechanics says facts exist only relative to systems. They cannot all be right. Most of them are almost certainly wrong. They disagree about whether the wave function is real, whether the universe branches, whether particles have positions, whether there are hidden variables, whether the collapse is physical, and whether there is an objective world at all. And every single one of them agrees on this. There is no place in the physical world where the theory tells you a superposition becomes a fact. Copenhagen refuses to answer. Many Worlds says it never happens. Pilot Wave says it never needed to happen. Collapse theories say it happens by a law we have not yet confirmed, and which the underground experiments are steadily constraining out of existence. QBism and relational quantum mechanics say it happens for you and not necessarily for anybody else. Not one of them says, here, at this point in the physical chain, at this scale, under these conditions, a single fact comes into existence in the world. That statement does not appear anywhere. It has never appeared anywhere. In a century of the most intensely scrutinized theory in human history, with tens of thousands of physicists and billions of dollars in experiments running under mountains, nobody has ever been able to write down where reality decides. And the reason is the reason von Neumann gave in 1932, and it has never been improved on. A theory made entirely of continuous evolution cannot produce a single event. You can move the cut, you can widen it, you can push it into the environment or out to the edge of the observable universe, you can relativize it to agents or duplicate the universe to avoid it, and the one thing you cannot do is find it, because there is nothing in the mathematics that could be it. Which leaves the terminus exactly where he put it, not because anybody wants it there, because the chain has to stop somewhere, and every candidate location inside physics has been checked, and they are all empty. The only place left is the place the theory does not describe. I want to bring this back to your body now, because there is a step here that people skip, and it is the step that matters. Right now, as you listen to this, photons are entering your eyes, roughly 10,000 billion of them per second in ordinary daylight, though the number varies wildly with conditions. They strike molecules of retinol in the photoreceptor cells at the back of your eye, and each absorption twists a single molecule from one shape into another. A change of a few tenths of a nanometer in the position of a handful of atoms. That twist is a quantum transition. It obeys the Schrödinger equation. It is one of the most thoroughly studied light-driven molecular processes in biology, and a single photon is enough to trigger it, which means your rod cells are operating at the absolute physical limit of what detection can mean. That signal becomes a change in the membrane potential of the cell, which is a matter of sodium and potassium ions moving through protein channels, and ions moving through channels is quantum mechanics as well, because everything is. It propagates down the optic nerve as a wave of electrochemical activity, it arrives at the back of your skull. Somewhere in the folded tissue of your visual cortex, a pattern of firing corresponds to what you are seeing. Every step of that is physical. Every step of that is describable, in principle, by the same equations that describe the particle in the laboratory. Which means that every step of that is inside von Neumann's chain, and none of it collapses anything, because unitary evolution does not collapse anything, ever, anywhere, and that is a theorem and not an opinion. And at the end of that chain there is your experience of seeing. One thing, not a superposition, not a distribution over possibilities. One definite visual field, right now, with one set of contents, which you have never in your entire life failed to have. That single fact, you're having one experience rather than a smear of them, is the only direct evidence any human being has ever had that process one occurs at all. Every measurement anyone has ever made in the history of science bottoms out in somebody having a definite experience of an instrument reading. That is the entire empirical base of physics, and it is the one thing the theory cannot produce from its own resources. The most successful description of nature ever constructed requires, as an input it cannot generate, the thing you are doing at this moment. I have been circling this for the whole of this script, and I want to say the uncomfortable version plainly, because I have spent a long time trying to find a way around it, and I have not found one. This is not the claim that your mind creates reality. I want to be as clear as I can. There is no evidence for that. The physicist most associated with it withdrew it. Decoherence explains without any minds at all why the world looks the way it does. And the whole idea is essentially extinct in professional physics. If you take nothing else from the last 2 hours, take that. The claim is much narrower and much harder to shake off. It is that quantum mechanics, as it is actually written down in the actual books, contains a term that refers to the occurrence of a definite outcome, that this term is undefined. That 94 years of extremely intelligent people have failed to define it, that the failure has been proven to be structural rather than accidental, and that the only place any of us has ever encountered a definite outcome is in our own experience. Physics has a hole in it, exactly the shape of the thing you are doing right now, and it does not know how to fill it, and it has been formally proven that it cannot fill it from inside. Von Neumann saw that in 1932, at 28 years old, and he wrote it down, and he was correct, and every serious attempt to prove him wrong since has ended by relocating the hole rather than closing it. Therefore, the last thing left to tell you is what happened to the man who found it, because there is an ending to this story that I did not go looking for, that I found while I was checking a date, and that I have not been able to stop thinking about since. In 1955, John von Neumann was diagnosed with cancer. The sources disagree about the specifics, and I am going to give you both rather than pick, because the disagreement itself is telling. Some accounts describe bone cancer, others pancreatic, and it is not clear from the record which is correct, or whether it was one that had spread from the other. What is not seriously disputed is the probable cause. He had been at the weapons tests. He had stood where the physicists stood, at Los Alamos and afterwards, in an era when the safety protocols around radiation were being invented by the same people who were being irradiated. The man who calculated the implosion geometry for the plutonium core was killed by the program he made possible. I do not think that is ironic either. I think it is simply what happened to a lot of them. He was 51 when he was diagnosed. He was, at that moment, a member of the Atomic Energy Commission, one of the highest scientific offices in the American government, and he held clearances that a very small number of human beings held. He went into Walter Reed Army Medical Center in Washington, and because of what was in his head, the United States government posted a security detail at his bedside, not to protect him, to listen. There was a serious concern that under sedation, under morphine, in delirium, He would begin talking about weapons design and deployment strategy in front of nurses and orderlies, and so armed personnel with the appropriate clearances sat in the room while he was medicated, monitoring what came out of his mouth. The formal terminus of the physical world, under guard, in case the terminus said something it should not. And he was afraid. This is documented by the people who were there, and it is the most difficult part of this to write about, because the accounts are unanimous and they are all about the same thing. Von Neumann, who had faced down every intellectual problem put in front of him, who had been described by his colleagues as the closest thing to a new species that anyone had met, could not face this. Wigner, his oldest friend, the boy he had walked home from the Fossori gymnasium with, wrote about it afterwards. He said that when von Neumann realized he was incurably ill, his logic forced him to realize that he would cease to exist, and hence cease to have thoughts. And then Wigner wrote a sentence that I keep returning to. It was heartbreaking to watch the frustration of his mind. The frustration of his mind. Not his fear, not his sadness, the frustration. Because the thing was a problem, and it was the first one he could not solve. And the instrument he had always solved problems with was the instrument being taken away. He asked for a priest. He had been baptized Catholic in 1930 at his marriage, and had not practiced. And now, at the end, he requested the sacraments, and they were administered by a Benedictine named Father Anselm Strittmatter, who visited him regularly through the final months. And by Strittmatter's own account, it did not work. Von Neumann was not comforted. He received the rites and remained afraid. His brother recalled that he passed some of the time reciting from memory the opening lines of successive pages of Goethe's Faust, page after page in German, from a book he had read as a child. The mind that could hold 44 volumes of world history was still holding them, and it was still going, and it was watching itself be dismantled from the inside, and it could not stop the process, or describe it, or accept it. He died on the 8th of February, 1957. He was 53 years old. He is buried in Princeton Cemetery, a short walk from the institute where he worked. I want to be honest about what I am doing with this, because I think it matters, and because you would catch me if I were not. There is no documented connection between von Neumann's death and his physics. He did not say anything on his deathbed about the measurement problem. Nobody at Walter Reed was thinking about Chapter 6. The parallel I am about to draw is mine, and it is interpretation, and you should hold it as interpretation. But I cannot look at it and not see it. Von Neumann's entire argument was that the physical description of the world does not close, that it runs out, that you can trace the chain from the particle through every physical link, and at no point does the mathematics ever produce a fact, and that the account only terminates when it reaches something that is not a physical system in the chain, something that simply has an experience and thereby makes it definite. He put the whole of physics on foundations that will never move, and then he showed that those foundations rest on a thing physics has no access to, and then that thing, in his own case, in a guarded room in Washington, came apart. Not metaphorically. The specific instrument that his entire framework depended on, the terminus, the place where description stops and experience begins, degraded in front of the people who loved him over about a year and a half while he watched. He knew exactly what was being lost. That is the part. He had written the argument that made it load-bearing. Nothing about this is finished, and that is not a comforting statement, because the directions it is moving in are worse than where it started. There are two things that could change the picture, and both of them are being actively pursued right now, and both of them are unpleasant in different ways. The first is that somebody finds spontaneous collapse. If a signal turns up in the next generation of underground detectors, or in levitated nanoparticle experiments, then process 1 is a real physical law, the chain is severed by nature at a definite scale, and von Neumann's problem is closed after a century. That would be one of the largest results in the history of physics. It would also mean that quantum mechanics as currently written is wrong, that the Schrödinger equation is an approximation, and that there is a new fundamental constant in the universe that determines how big something has to be before it is allowed to be a fact. Every experiment so far has come back empty, and the allowed parameter space keeps shrinking, which is to say the most hopeful outcome is currently losing. The second is stranger. The Wigner's friend experiments so far have used photon paths as observers, and everyone involved is careful to say that this only tests the logical structure. But the physicists working on this have been explicit that the natural next step is a friend that actually processes information and reports on what it found. Cavalcanti and Wiseman have discussed this openly, and the target is a sufficiently large quantum computer running an information processing system inside a coherence superposition, which is asked afterwards whether it observed a definite outcome, and which is then reversed, undoing the measurement, and asked to demonstrate that the superposition was never broken. Think about what that experiment would consist of. You put something inside a machine, it observes a result, it tells you it observed a definite result, and then you run the machine backwards and prove that the definite result it reported never actually happened in any absolute sense, and the thing inside remembers nothing, because you erased the branch where it remembered. Nobody has done it. The engineering is far beyond current capability, by many orders of magnitude, but it is not a thought experiment anymore, it is a roadmap in the literature, and the theoretical work defining what would count as a friend has already been published. And when I read that, the thing that struck me was not the technology, it was that we have arrived, entirely by the internal logic of a 1932 proof, at the point where the only way to settle the question is to build an observer and then take it apart to see whether its observation was real. Von Neumann's chain has become an engineering program. Here is where it actually stands, 94 years after the book, in the plainest terms I can manage. We have a theory that works perfectly. We use it to build everything. It has never made a wrong prediction. And it contains a step, right at the point where it touches the world, that nobody can define, that has been proved cannot be derived from the rest of the theory, that has been searched for in every physical system from a single atom to a molecule of 2,000 atoms to a mountain full of germanium, and that has never been found anywhere. The chain runs from the particle to the detector, to the light to your eye, to your nerve to your cortex, and the mathematics does not stop at any of those places, and the mathematics is right, because we have checked it more carefully than we have checked anything else in the history of the species. And then it stops. At you. Not because you are special, not because your mind reaches into the world and rearranges it. There is no evidence for that, and the people who once believed it took it back. It stops at you because you are the only place anyone has ever confirmed that a single definite thing occurs, and because the theory has no term for whatever it is that you are doing when that happens. Every single fact that physics has ever established, every measurement in every laboratory in every country in every year since Galileo, entered the record through somebody having one experience of one instrument. That is the base of the pyramid. Everything else is built on it. And the base has never been described. You are the undefined primitive at the bottom of physics. That was the thing I asked you to hold on to at the beginning, and here it is, and it is worse than it sounded then. Because now you know that it was proved rather than assumed, that the proof has stood for 94 years, that every attempt to root around it has cost more than it saved, and that the man who found it spent his last months under armed guard in a hospital in Washington watching. The very thing his argument depended on come apart, reciting Faust from memory, afraid, unconsoled, unable to solve it. The chain is still running. It has been running through your nervous system for the entire time you've been listening to this, and it is running through it now, and every equation we have says it does not end. But you are having one experience. Right now, definite, singular, unmistakable, and the only one available to you. Nobody in 94 years has been able to say why,